Welcome back. Okay, so I hope you enjoyed the game show. Now we're going to be looking at some definitions and actually going through the process of integrating. So the antiderivative, the reverse operation of finding a derivative, is called the antiderivative. A function f is an antiderivative of a function f if, when we take the derivative, we get this as an answer. So remember when we did the x cubed, right? If I take the derivative, if I take the derivative of x cubed, I get 3x squared. Okay? So this is the derivative. This is the antiderivative. Okay? The antiderivative is the original function. But I'm actually going to put up a screen here for a second to cover up a few different things. What if I have this as my function? X cubed plus 7. And I take the derivative of that. Well, the derivative of x cubed plus 7, we take the derivative of the x cubed and we take the derivative of the 7. Well, the derivative of x cubed is 3x squared. How about the derivative of 7? Well, the derivative of a constant is just 0. So we get the very same derivative for x cubed plus 7 as we did for as we did for x cubed. They have the exact same derivative. And now you've learned one thing about the antiderivative. Okay? And that thing is that when we have, so if a function has more than one antiderivatives, the antiderivatives can differ by at most a constant. So there's actually an infinite number of functions that have 3x squared as their derivative. All of them include x cubed and some constant. So no matter what the constant is, if I take the derivative of x cubed plus some constant, I'm going to get 3x squared. Okay? Here's another example. So we want to find the antiderivative of f of x equals 5. What functions have 5 as their derivative? Well, 5x, derivative of 5x is 5, and the derivative of 5x plus 1, oops, that's a plus 1, is 5. And matter of fact, the derivative of 5x plus any constant is going to be 5. Okay? Find the antiderivative of x squared. Okay? Right? Well, there are several functions that have the derivative of x squared. Okay? So if I have x, for example, here we have some right here. We have 1/3 x cubed. We have 1/3 x cubed plus pi. We have 1/3 x cubed minus e. We also could have 1/3 x cubed plus, what's your favorite number? 17. Okay. If I take the derivative of any one of these, so the derivative of 1/3 x cubed, okay, would be 1/3 times, the 3 would move in front, so times 3, x, and then we would reduce the exponent by 1. 1/3 times 3 would give us 1, so we would have x squared. And we'd get the same thing for any one of these. So the derivative, for instance, of the one I wrote here, of 1/3 x cubed plus 17, okay, we would have 3 times 1/3 x, and this would be reduced by 1, plus the derivative of 17 is 0, which would give us x squared. So there are an infinite number of functions that will have a given function as its derivative, and every one of them will differ by at most a constant. So here we have a bunch of functions whose derivatives are 2x. Okay? So functions that have 2x as its derivative are x squared plus 1, x squared plus 3, x squared minus 2. As a matter of fact, they're all graphed there. Right? So in black here, we have x squared plus 3. And in red there, we have x squared plus 1. And in blue, we have x squared. And in sort of green, kind of aqua-y color there, we have x squared minus 2. Any one of those functions, we take the derivative, we're going to get 2x as our answer. Okay? So the antiderivative for 2x is any one of those. X squared plus 3, x squared plus 1, x squared minus 2, and actually x squared plus c, where c is any real number. Okay? These are called a family. These are a family of functions here. They're sometimes called the general antiderivative. Okay, so the general antiderivative are a family of functions with a given derivative. But derivative looks a little strange there. Let me try to make that a little nicer so you can actually read it. They do differ by only a constant. So when we're taking the antiderivative, the indefinite integral, the indefinite antiderivative, we do need to note that these could differ by a constant. We can't account for that constant because we don't know what constant was there. Because you go and take the derivative of a constant, it's 0. So it's erased, right? I don't know if there was a constant when I took the derivative and got 2x. Because if there was a constant, the derivative of any constant is going to be 0. So I don't know if there was a constant. So when we take the antiderivative, we don't get a single answer. We get a family of functions. And that's why it's called the general antiderivative. Okay, so the indefinite integral. Okay? So when we take the derivative, the integral, so used to us doing derivatives, now I have to say integral. Now we're switching gears here. So when we take the integral, we don't have a single answer because the derivative of any constant is just 0, right? So the derivative of a constant is 0. So any constant that might have been there is gone. Okay? So because there could be a constant that we don't know about, we can regard an indefinite integral as representing an entire family of functions. One antiderivative for each value of the constant c. Okay? So we put a plus c in there because they can differ by a constant. There could be a constant there that we don't know about. Okay? Okay? So for every antiderivative, f must be of the form g of x plus c, where c is a constant. So every time every single time we take the indefinite integral, we must include c as part of the function. And the c stands for constant. Okay? So because we can differ by a constant, we have to include that every time we do the indefinite integral. All of these that we're doing right now are the indefinite integral. Okay? I will tell you when we look at definite integral, and it will look different. It will look a little bit different. Okay? All right, so indefinite integrals. Let f of x be a function. The family of all functions that are antiderivatives of f of x is called the indefinite integral. It has the elongated s symbol there. That's called an integrand. So integrand f of x dx. So the symbol, the symbol s there is integral sign. The function is the integrand. And the symbol dx indicates that the antidifferentiation is performed with respect to the variable x. Okay? So by the previous theorem, if f of x is any derivative of f, then the integral of f of x, of some function, is going to be the antiderivative plus the constant. Okay? So every single time when we take the indefinite integral, okay, we're going to have the function whose derivative is our given function plus this constant of integration. Okay, so c is called the constant of integration. We have to include that. If you forget the c, it is incorrect. So don't forget the c. That's all. Just remember it. Okay? And I think a lot of this begins to make more sense the more that we work with it and you get practice with it. Okay? But I'm hoping that it makes sense that because when we take a derivative of a constant, we get 0, okay, we have to represent all of the possible constants here. So whenever we have this group of functions here, they all have 2x as its derivative. We want to make sure that we note that there's not just one function, there's a whole family of functions. Okay? All right, so where do we leave off? Excuse me. We did that one. All right. And we left off any day now. Right there. All right, so now some rules. Okay? So now we're going to go over some steps. Okay? All right, so power rule for the indefinite integral. Okay? So if we have some function raised to a power, okay, so n is just some number exponent. So long as that number exponent is not -1. We have a different rule there. If you remember from our game, what's my function? When n is -1, it is not going to be the power rule. Okay? So if n is anything but -1, okay, to find our function, our integral, our antiderivative, the function who has a given function as its derivative, okay, we're going to undo the power rule. So that's basically what we're doing. We're undoing the power rule for derivatives. We're going the other way. So if you remember when we took the derivative, okay, so we're going to take the derivative of x to the n, okay, where n is some number. Okay. The n moved in front, and we decreased this by 1. Right? That would be our derivative. Right? So we have to undo that. To undo that, we have to add 1. To undo the fact that we move the exponent in front and have a coefficient, we have to divide by that n there. Okay? So now we're undoing this multiplying, and we're undoing that reducing our exponent. We're going to undo that part. Okay? And we're going to undo it by adding 1 to the exponent and dividing by n plus 1. Essentially, whatever this exponent is here, this is going to be the same thing. You're going to divide by whatever that exponent is. It undoes the fact that you moved something in front. It undoes the fact that you reduced the exponent. So for instance, the antiderivative, the integral of x cubed dx, would be x to the 4th divided by 4 plus our constant. Can't forget our constant. Okay? So all we've done here is we've increased the exponent by 1, and we've divided by that same value, which would give us x to the 4th divided by 4 plus c. The nice thing, like I said earlier, about integrating is you have the answer. So you can check yourself. The answer is x cubed. If you want to check yourself, take the derivative of x to the 4th divided by 4 plus the constant. Okay? So we take the derivative of x to the 4th divided by 4. We would have, the 4 would move in front, so we would have 4 times x to the 4th, and we reduce, oops, I better not put the parentheses around both those things, otherwise I'm going to be raising 4 to a power. Okay, so if we're taking the derivative, the 4 would move in front, and we decrease the exponent by 1. And then we would take the derivative of our constant there, but the derivative of a constant is just 0. Okay? So now we've got 4 times x to the 4th. That's going to be just an x. Excuse me, 4 times x over 4, 1/4 x, is just going to be x. And then the exponent now is just going to be x cubed. Okay? So you can always take the derivative of your integral and check yourself. If you take the derivative again, do you get this number again? If you don't get that number again, you've made a mistake. Maybe you forgot something. Okay? But if you just follow, I mean, the rules are pretty easy to work with. And the first one is the power rule. All right, rule number 2 is our what happens when we have x to the negative 1. Okay? So anytime we have x to the negative 1, okay, this one is not a power rule. I don't know why I really shouldn't have power rule up here. I guess it's not really a power rule, but it doesn't really have a better name. So power rule, but this is the one for when we're looking at exponential and log, as opposed to polynomial. I didn't put that heading there. The formulas are the formulas. So if we're taking the integral and it's x to negative 1 dx, right, or 1 over x dx, okay, that is natural log absolute value of x plus c. Make sure you include those absolute value bars. This has to be positive. Okay, so for e to the x is one of the nicest functions you can ever think of. It's its own derivative and its own integral. So the integral of e to the x dx is e to the x plus our constant. Okay. And the integral for b to the x dx, so this time this is an exponential function. This is where our exponent's a variable, is going to be our function, b to the x, divided by natural log of b. Because remember, if we were to take the derivative of something to a power, let's put 2 to the x. Okay? So if we were to take the derivative of 2 to the x, okay, it would be 2 to the x divided by natural log of 2. The only one that didn't have the divided by natural log was e to the x. Right? Because the natural log of e is going to cancel itself out, and you're just going to be left with 1. Right? So to undo, if there's nothing there, oh, oops, sorry, I have one little oopsie there. I just realized, not divided by 2 to the x natural log of 2. Sorry. I'm looking at my integral there, and it swayed my answer to put the natural log of 2 underneath. And the natural log of 2 belongs up right next to it. It's not divided by natural log of whatever our base is. It's times. Sorry about that. And so now if we go the other way, okay, right, so if I were to go the other way, and I have the integral of 2 to the x dx, my answer is going to be 2 to the x divided by natural log of 2. That would be the integral. Now let's integrate that. Okay? So if I integrate 2 to the x, oops, excuse me, not integrate, differentiate. So if I take the derivative, I'm going to mix those words up and say the opposite, I think, all day today. So just note what I'm doing. Here I'm taking the derivative. Even if I accidentally say integral, I'm taking the derivative. If I take the derivative of 2 to the x natural log of 2, okay, that would be 2 to the x natural log of 2. The natural log of 2 is just a constant. Right? So constant multiple rule, if this helps you out. That constant multiple is just going to stay. When I take the derivative of something times, some function times natural log of 2, I'm going to have some function times 1 over natural log of 2. I'm still going to have that 1 over natural log of 2. That's just a constant multiplier. Times the derivative of 2 to the x, which would be 2 to the x natural log of 2. And look at that, those cancel out. And that gives me 2 to the x, which was the one I started with. Okay? Right, so in the beginning, these might be tricky, just like taking the derivative was tricky for you. But now taking the derivative, not so tricky for you. Okay? And especially as you work with your rules and write them down and refer to them, and then they'll start to be ingrained in your head. Okay? And I think I'm just going to go over 2 rules, and then I'm going to stop this tape so it doesn't get too long, and then I'll go over some examples. So sum and difference is the same as when we're taking the derivative of a sum or difference. So the integral of a sum or difference is the same as the integral of each of our terms. So if I have the integral of f plus or minus g to the dx, I have 2 functions here. I can take the integral of the first function and the integral of the second one, and so forth. So for instance, the integral of x squared plus x to the dx, I take the integral of x squared to the x squared dx, plus I take the integral of x dx. Both of these are power rules. Okay? So I'm going to increase the exponent by 1 and divide by that same number. Right? So the integral of x squared is x cubed divided by 3. The integral of x is x squared divided by 2 plus our constant. And we could check ourselves. So the derivative of x cubed divided by 3 plus x squared divided by 2 plus a constant would be the derivative of x cubed divided by 3. So that would be 3, the exponent would move in front, times x divided by 3 to the, and we reduce the exponent by 1 squared, plus, take the derivative of x squared divided by 2, 2 moves in front, reduce the exponent by 1, so now that's going to be to the first power, and the derivative of a constant is going to be 0, and then if we reduce, this would be x squared plus x. Oops. And the most horrible looking x there. Sorry, x squared plus x, and that's exactly what we have here. It matches. Okay? So just some practice with the power rule. And so sum and difference just means that you can take the derivative, the integral of each one separately. Constant multiple rule. Okay, so if you have some coefficient in front, don't have to worry about it. You can just pull the coefficient out, right? Because when we take the derivative, we would multiply it by whatever coefficient was in front. It's not going to be affected. So we can pull that out, that coefficient in front of the integral, and then take the derivative of our variable here. Okay? So the integral of 2x cubed dx would be 2 times the integral of x cubed dx. We increase the exponent by 1, and we divide by n plus 1. So now we've got 2 times x to the 4th divided by 4, plus our constant of integration, and we can reduce that, the 2 and the 4 reduce, x to the 4th divided by 2 plus c. And if we take the derivative of x to the 4th divided by 2, I'm actually just going to write that as 1/2. 1/2 x to the 4th plus c. Right? So the derivative of 1/2 x to the 4th would be 4 times 1/2 x to the, reduce it by 1 cubed, and then the constant would just be 0. Oops, 0. And so 4 times 1/2 is going to be 2x cubed, and that's exactly what's here. Okay, so that's kind of the nice thing about integrating is you can just check your work by taking the derivative of your answer, and you should get the exact same thing again. You should get what you started with. All right, so I'm going to stop here, and then we'll look at some more examples in the next podcast.